So the screen that I shared, is that visible? Like,
Yes, yes, sir. It is visible, sir.
okay.
Yes, sir. Screen is good.
Yeah. So that's 1 minute. Okay. So now we'll be starting some learning by programming. Okay. So I hope all of you. What's the problem? Just give me 1 minute. There is some problem with the sharing thing. Let me do it again. So I need to follow the chat, right? Um,
Sir, I am able to see your screen.
yeah, you are able to see my screen. I just need to reorient the chat screen, and all people are asking questions.
Acha, acha. Okay, okay. Okay, sir.
Um, so basically, I'm using multiple display.
Mm-hmm.
Sorry. Yeah. So those I hope many of you or all of you will do programming with me. You do not need any prior thing. So just open your either Google Colab or whatever environment you have, because you already are doing a lot of programming through this QT-01, 2, 3, and other faculty members like Dr. Jai Kumar and others. So you have something. So we'll do the probability things in Python, as the name of this course is programming lab or something. So I thought to cover some programming sessions here. So basically, let us do some. So to do this kind of experiments, first we need to install certain things. Let me install the packages. So you just need to do these things. So pip install, because you will be using NumPy, SkyPy, Matplotlib, and Qiskit. So for the time being, I'm removing the Qiskit part. Today, I'm not going to the quantum part. Tomorrow, I'll cover some examples of the stuff that is important in the quantum stuff, specifically for random number generator and other things. Today, for the time being, we limit ourselves within this probability and state itself. So NumPy is for the numerical computation. SkyPy is for the scientific computation, and Matplotlib is the library, Python library for this plot, like MATLAB kind of plots, okay, figure generation. So you just need to install this. I think those who are using the Google Colab, they already have these things. Okay. So now we need to import certain libraries. Okay. So for example, this whenever you have already installed these things, then you just need to import. So we have imported the numerical library NumPy as NP in the short form. Similarly, matplotlib.pyplot as PLT is a short form for this entire library. Then we have the SkyPy library. From that, we have imported certain distribution functions: binomial, Poissons, uniform, how to calculate the norm of some variable, mode, chi-square distribution, linear regression, beta, etc. Okay. So don't worry about all this distribution. Even if you haven't covered, I'll share some notes for these things. I hope many of you already have covered these things. So once you run these blocks, you can run with me. You can, okay. So, uh, so once it is done, just somebody uh, confirm in the chat, okay? Because I'll just scroll the screen. Now I will first do the experiment for toss of a coin. I will just take 1,000 number of tosses. I call the random function from the NumPy library, and then random number has only choice 0 and minus 0 and 1. These are the random variable here, 0 and 1. and the probability should be ideally 0.5 and 0.5. And you can also calculate the probability by just by writing the values. Okay. So once I run these things, then do some plotting of this PMF probability mass function. So this is how you generate the probability mass function for two random variables 0 and 1. Okay. So these are pretty much standard, like as those who already know MATLAB. So this is just similarly PLT dot all those same comments. Okay. Here only I have done is that even if I compute the binomial distribution for 0 and 1 for 1-1 trial, right? So 1-1 trial for the binomial distribution is like the Bernoulli distribution with 0.5 probability, right? Suppose you take 10 trials, okay, and you change the probability, okay, say 0.3 and 0.7. You can do this. So you can see that how many number of like probability of the head and tails in this particular case after doing the 10 trials. Okay. So now let's do some stuff for rolling a die. Okay. So I have already written some code. I'll explain the code and I'll share the file. Don't worry. But if possible, try to write at least some of the things with me. Okay. So this is not required. Okay. So I will take 100 coins and random choice between 0 and 1. This is already I have done, right? This is not the case, so I have to do this one. So now I'll toss a die, and tossing a die for 1,000 times, and that will take random numbers, integer random numbers, that is np.random.rand int, integer random number. If you remove this int, basically it can take any values. Okay. So it will take any value between 1 and 7 with integer values and number of toss or number of rolls. And it will calculate the empirical probability mass function, that how many times it is repeated with the total number of count, that is the frequency definition of probability for all such counts. Okay. So let's see what is happening. So theoretically it should come all as 1/6, right? That is roughly 0.15, but so basically point actually 0.166 something approximately, but that is a theoretical empirical one. But actually in the histogram you see that PMF is a bit different. That is coming from the because you are repeating the experiment for small size. Say you do it for 10,000 times trial, and you see almost the probability distributions are coming closer enough. Now if you just reduce the experiment to 100 times, you can see that the probability is even more poor. It is in fact not the uniform distribution, right? So your theoretical formulation is not matching with the number of with the distribution of the PMF. Okay, so that's why we do quantum repetition more and more, so that we get a best estimate of the outcomes, right? The distribution as correctly as possible. Okay, now let's see some of the shall I wait here? Anyone doing the coding? I can wait here. You can just try the code from yourself, change the values and all. At least you write this code, this part of the code. This part is just everywhere it is pretty much same. Okay, shall I share the code in chat? That I can do. And let me know if you face any difficulty even going to the CDF part. So let's first try the normal distribution. So let's take a zero mean with standard deviation 1, and let's generate the x values. So np dot lean space is the function to define the x values. So basically it's the functional values.
चल सर
Sorry,
हाँ हवा चल रही है अरे यार
somebody
आधा ही बचा है अभी तो आधा ही बचा है घूम फिर रहा होगा नेट नहीं चल रहा होगा और क्या
okay. So so let's first calculate the PDF and also calculate the CDF and their plot, how it is coming. So for this PDF thing, I have called normal distribution norm.pdf. I have put the x values. These are just lead space corresponding to these values and with 500 points. So you can change the number of points as well to see, I mean, more like, because anyway, you are designing a continuous random variable on a computer, but these are essentially discrete. So by increasing more and more sample points, it looks good. So then if we run this part, so let's first try to generate the PDF of the normal distribution. So plt.figure the same comments and the PDF values we are printing here. So this is the normal distribution plot, how it looks like. So let me try this comment whether it will work or not. Check the np dot this main of this. Yeah. So I can see also the mean of this distribution, like so. So although I started with the zero mean thing, you can check here. I started the normal distributions with 0, right? Let's increase but after this theoretical, from the definitions to the plotting, now I just check with the simple calling functions, and they are not same, right? So let's draw the CDF. So you can see the CDF looks like this. So if you do the basically the derivative of this CDF function, you will get the PDF, this one. If you do the integration of this, you will get something like this. We can also calculate the probabilities in the interval from the PDF and CDF. So the comment for that is that probability between the from the CDF we can compute the probability, that is the difference between the CDF values between 2 points, right? And the probability to get from the PDF is basically the multiplications, that integrations, right? The fx dx. So basically probability x between -1 and 1 is basically 0.6827. Probability is that is less than -2, right? So that is 0.022. So that means what is from the normal distribution between -1 to 1. So this point to this point. So the region in this side here. So this area, the value of this particular area is the probability, that is 0.68. So in statistics, this is like this is something called I am not sure, like forgot, like it's probably the 95% confidence range or something like that. So in statistical inference theory, then let's do some descriptive statistics. So I do mark down or text to write the text and then coding for the coding part. So to do this thing, so let's take some data, right? And let's calculate this basics thing. So I take a array it's a vector or array, np.array, and I took certain numbers 12, 15, 18, 12, 20. These are some random numbers. And I'll calculate the mean. To calculate the mean, you just need to do np.mean. To calculate median, so that is the highly dominant number in the sorted list of this, right? np dot this median, and then the mode, which number has highly repeated and all, and counting from that, so mode. So these are like the statistical definitions: mean, median, and mode. So you can calculate that. And also we can calculate the variance, the second order statistics, variance, and the standard deviation as well. And then basically see the result. So to calculate the variance, np.var is the command. np.var is the function name, and we are importing the data as the argument of the function from here, right? Similarly, standard deviation is np.std, and you can now print all the data, their mean value, median value, mode, variance, standard deviation, and all. So the expected value is the, so let's check. So we have taken the sample data from like 12, 15, and all this from these random numbers. We calculated the mean is 16.67, median is 15.50, mode is 12, and then basically we have calculated the variance, standard deviation, and we have checked these values for the expected value from a die and the variance from a die experiment, like basically tossing a die, six-sided die, right? And the definition is here, like expectation of x square minus expectation of x whole square, right? So these are just definition. I haven't like covered. These are very basic. So I'm just showing examples for those things. So you can simply try this thing. So I'm sharing the code. You can try and let me know whether it's working or not. Or if you have any doubt, you can ask me. So one question got right. I shared the code in chat. You can check from there. Okay, this is just how this x is defined. You can take a different x like np.link space np.arrange from 1 to 9, 1 to 10. This is how just it is defined. You can different in a other ways this x. Okay. Then let's do experiment for, okay, there is something called the central limit theorem, uh, and laws of large number, right? So it says that if you have independent variables that is coming independent and basically outcomes from an experiment, and if you do not know any prior distribution of that functions, right, how it is following the randomness, but if you just repeat that experiment for very large number of times, then it follows the Gaussian distribution. So okay, let me write it as a text. So central limit theorem states that the distribution of the samples means of a sufficiently large number of samples, each from the same independent distribution, will be approximately normally distributed. Let's check this theorem. So let's take 10,000 number of samples and number of samples and then samples. So basically number of times we take the sample mean 10,000 and number of die rolls in each time n. So suppose we do the basically die tossing, like rolling the die experiment for 10,000 times, right? So basically let's check uh, whether it is following the central limit theorem or not. It's difficult to convert the PDF code that is in this particular code where I am writing, I can share this Python file later, but I do not have any PDF. Okay. So see, this is the plot of sample mean versus the density. Okay, the probability density. Now you can see that if you decrease the number of samples, say 100, okay, so only few points. So this is no more. You cannot say that this is a normal distribution, right? So this definition is only valid for large number. Say you take 10,000 such realizations. Now you can see this is at least the most of the like appearance of the structure is following this normal distribution. Most of the energy of these values are concentrated within this normal distribution. So let us increase these points a bit more, say 25,000 maybe. Okay, maybe 50,000. Still not that great. Okay, maybe 1 lakh. Okay, so I mean, okay, let me increase the number of these samples as well, independent. Let it be 100. Yeah, now it is coming. So it's just not the number of times we take the sample mean, but also how many number of die rolls we do independently. Okay, so that will give us some good approximate of the function altogether. So now let's take some the probability distribution function with some of our real life examples. Okay. So I again I called all these distributions. So let's understand something called the Poisson distribution, and that is I think one of the most important in network theory and daily life examples. It's something like this. So so in the last just in the last lecture we have seen that the binomial distribution success probability versus the failure probability thing, right? Here is some parameters like that, and that is called the lambda. So lambda is the average rate of occurrence. Say for example, number of customers arriving at a checkout counter in a supermarket per minute. How many customers comes, or how many? So suppose you reach to a metro, and so how many metro train you see in 5 minutes or 10 minutes, right? So this kind of process, okay? Or what is the probability that if you reach between 3 and 3:30, that you will get a flight from your city, right? So this kind of discrete probability notion and the distribution is defined with the Poisson distribution with the parameter called lambda, okay? And that is defined as lambda to the power k into e to the power minus lambda by k factorial, where k is the number of number of occurrence, how many times it's happening, okay, and lambda is the average rate of occurrence. So let's do a example here. Okay, PDF code. I mean PDF means probability density. Yeah, probability density. Okay, I'll share the code. Asking probably for this normal distribution. Let me copy and paste. Okay. So now let's take this example. So we take the average rate of customers that appear in a particular shop is 3 per minute, and possible number of customers arriving is between 0 and 10. Okay, and we need to calculate the PMF for each such K, like possible number of customers arriving that particular K that can take any value between 0 to 10. So through this Poisson distribution, so let's check it. We'll calculate like sample mean from 1,000 some Poisson examples. So this is the Poisson distribution where that X is lesser equals to 3 customers, that probability. So number of customers arriving K. So this is the 0, 1, 2, 3. These are the number of customers, and Y-axis is the probability. So if you want to calculate that at least 3 customers comes per minute, okay, so the probability is 0.6432. So you just need to add this plus this plus this. So if there is lesser equals to, then you need to add this probability as well. So 0 plus 1 plus 2 plus 3. Probability of 0, probability of 1, 2, and 3. Also, you can calculate the mean from your density function. So that density function is this one. So if, sorry, I mean mass function. So if you know the mass function, lambda to the power k, e to the power minus lambda k factorial, and if k varies, right, times this x. So that will give the PMF. So from that, you can also calculate this plus this as this 0.6472. Now sample mean from thousand such Poisson samples will be 3.03, and you can also calculate the variance of this particular problem. So now let's take a geometric distribution problem. So sorry. So geometric distribution models the samples of Bernoulli distributions trials needed to get the first success. It assumes that, so if I repeatedly trial something, so suppose I try tossing a coin. So what is the number of trial that I should do such that I get the first head or first tail for the first time, right? Suppose I appear for the UPSC exam multiple times. So what is the probability that I'll success? How many trial I should try? Okay. So it assumes each trial is independent. So in this particular case, there is no impact of the previous trial, and it has the same probability of success P every time. So that probability X equals to K. That means K is the number trial. Okay, equals to 1 minus P to the power K minus 1 into P. This is the probability mass function, where K is the number of trials and P is the probability of success. So number of attempts a student makes to correctly answer a multiple choice questions, okay, until they get it right. Assume the student guessing. So a student is answering a MCQ questions randomly, okay. So what is the number of attempts that the student makes a correct answer? So assuming that the success probability is basically 0.25, okay. So now let's calculate that. So success probability 1/4 definitely. Now we use the geometric distribution to check that how many trials it should try to get the first answer correct, right? So this is the geometric distribution. So if one attempt, the probability is 0.25. If the second attempt, it attempts 2 times, the probability decreases to 0.18. If 3 attempts, it does probability 1/4. Fourth attempt is 1/0. So what you can see is that more times you do random answer in your MCQ questions, and you think that, okay, I tick 4 questions, one of them will be correct. The probability is growing less and less. Okay, from the distribution you can see. And if the probability of X less than 3 items, so that is on an average 0.5 total. Okay, the sample means from 1,000 such geometric samples, each 4 should be close to 1/P. So more random answer you try, more chance that you will make mistakes. Okay. This is called the geometric distribution. Now, let's try one continuous distribution function. Earlier I tried the normal one, and now let's take the exponential distribution function. So the exponential distribution function describes the time between events in a Poisson process, a process in which the events occur continuously and independently at a constant average rate, right? And so x is the time. So earlier it was the Poisson distribution or the discrete distribution, and the definition was this one. Now you have a more variable, second variable. What is that variable? X. What is x? X is the time elapsed between two events, x greater or equals to 0. And lambda is again the rate of the parameters and mean of the distribution 1 by lambda. Okay. So suppose the time in minutes until the next customer arrives at a busy stop, busy coffee shop. Assume customers arrive at an average rate of 0.5 customers per minute. That means one customer in every 2 minutes. Lambda equals to 0.5. Okay. So basically, 1 by lambda is basically your like average customers per minute, right? So then let's calculate certain things. So lambda is 0.5. That means corresponds to the mean of 1 by 0.5 equals to 2 minutes average, right? And you calculate certain x values. This is just np.lim spans between 0 to 500 with increment 10. These are some points. And we calculate the PDF using the function ex on.pdf, and we just plot it. So what we get is some functions like this. This is the exponential function. So probability of x lesser equals to 2 minutes is 0.6321, and more than 5 minutes is 0.821. Sample mean from 1000 exponential sample is 2.04. So these are the various calculations you can get for 1000 such sample points for the mean, variance, and other things. Okay. Then okay, I'm not going to the uniform distribution, but what I'll do, there are some more distribution, but let me now introduce something which is more important, that when some distribution is used and when something is not used, okay? And how they are related. So interplay and convergence of probability distribution, when one distribution converges to other distribution. So in many cases, like probability distributions are related, and under certain condition, one can be approximated by the other. Okay. So for example, the binomial distribution, when it will converge to Poisson distribution. So basically in binomial distribution, what are the parameters? N and P, right? Now N is what? N is the number of trials, and P is the success probability, and 1 minus P is the failure probability. If the case is that you have N into P, that uh, you tried certain times and you got some probability, such that multiplication of N and P, that is the number of trial and number of success, is some constant. It is not changing much. Okay. So then basically that means say for example 500 times you have tried and you are getting 50% probability, something like that, and that rate is almost same. Then you tried 1,000 times and you got 500, you got 2,000 times and you got 1,000 times success rate. You tried 1 lakh times, you got success in 50,000 times, something like that, or close to that. Okay, such that the multiplication is constant. Then binomial distribution can be approximated by Poisson distribution. Say for example, let's take something, and also in this case there is one more constant, is that so when the number of trials n of a binomial distribution is very large and the probability of the success is very small. Okay, this is one more constant, such that n into p is lambda. Okay, say let's take lambda value 5, and then basically this n1, n2, n3, we are taking several cases like 100 trials, 1,000 trials, 10,000 trials, various cases, and we'll see like whether n into n1 into p1 is lambda constant or not. Okay, so you see there are various cases like binomial distribution with 100 points and 0.05 probability, 1,000 points with 0.005 probability, and this is the case where probability is much less, number of trial is more as compared to the probability values. Then this n into p becomes lambda. Binomial distribution converts to the Poisson distribution. Now let's check something. I mean, let's change the value. Say for example, the first case, you have taken 100 sample, and let's take the probability value is like lambda by say 2. Okay, and now let's check the answer. You see that disappear probably. So in the plot, so let's take this is by 20 maybe. See, this is not at all a Poisson distribution. So that is how it is different. Like um, and say so basically you change the number of trials again, and again you will see the result is very poor. It is in fact following some exponential distributions, right? So that's why this is important that your n is very high, but your this probability is very less than n into p is lambda, and this is verified here. Okay, so this is one particular case, and second particular case is these are important. I mean, this is especially important when you do analysis of errors and all. You suppose you get a quantum information very less, okay, and you do a lot of time, a lot of qubits you have used, so your random variable space is very high, okay, and your information content is very low, whether you can approximate to that particular distribution as a continuous or not, which distribution is that. So these are some questions. Okay, so now binomial distributions can be approximated by the normal distribution under condition, and the condition is when the number of trials is sufficiently large, but probability is not too less. I mean, it is not too close to 0 or 1, right? Such that these conditions are maintained, then binomial distribution approximates the normal distribution. So this is the binomial distribution. So basically out of n trial, k is the success. So nck p to the power k 1 minus p to the power n minus k. This is the success probability. This is the failure probability. And this particular probability mass function, where it is a discrete variable, a discrete random variable probability mass function, and it is a continuous one. You can see the interplay between discrete to continuous, continuous to discrete. Why I am showing these things? These are very basics, but these are very important to quantum computing. In fact, any other engineering domain where your physical noise is continuous, but appearance is discrete by measurement, right? So how you can approximate your information, your content, right? So these are the things which are important to model, analyze your the result. Suppose you apply certain quantum algorithms, you get some estimate, some parameter estimate of some parameters. How you will quantify that information is correct up to this with this much error variance and all. So then basically you need to model your noise, you need to quantify that, you need to calculate the bound, and this kind of interplay will help. Okay, so let's take an example for this. So okay, math is not defined. I have to define the math variable. Where is math? I don't know. Let's try uh, import math from maybe from Skype. Is it the case? No, it is not available in Skype library. Let's take from NumPy maybe. Still not available. Okay, just to give me a couple of things. I can directly import math probably. Math is a library, maybe the case. Import math. Say. Correct. So I take this binomial distribution with 100 points and probability 0.5, and then basically I can see that the distribution, this blue color, sky color things, is approximated by the normal distribution, right? Again, here I have taken 200 points and probability equals to 0.2. Then I can see the distribution, binomial distribution, they can be approximated as a continuous random variable normal distribution, or the Gaussian distribution, I should say. So let's take suppose this is equals to 0.5 and this is equals to say 20. Now see, this is like almost varied, and you can change more. Maybe this can be 200, and this can be say 0.99, very close to 99% chance. So this is no, I mean, the approximation is very poor. Okay, so mean is at 198 and sigma is 1.41. It's a not normal distribution. It's a some distribution. Okay, we can call some Gaussian distribution, but the approximation is very poor here in this particular case. So okay, so you can interplay, like if you take various such values of this distribution points and check like how one particular distribution is converts to a second kind of distribution, like especially discrete to continuous and continuous to discrete approximation is critical in analysis. Okay, um, and then probably the last one, this is the thing I have done. And the last one is basically Poisson to normal distribution. This is another discrete to continuous random variable approximation. Okay. So basically, so in a case where lambda tends to infinity, okay, so the Poisson distribution can be approximated by the normal distribution when lambda is sufficiently, the rate is very high. The rate of occurrence of something is very high. In that particular case, mean will be equals to lambda and standard deviation will be square root lambda. And that particular situation, let's take this particular Poisson distribution can be approximated with this um, Gaussian distribution, okay, or the normal distribution in the special case. Okay, so let's take an example for that particular case. So I will take lambda Poisson small and lambda for the Poisson's large, these two particular case. Okay, there is some question. Which PDF or CDF relates most of the noises or errors in quantum algorithm implementation, or which event in quantum algorithm experiments each of these CDF PDF relate? Okay. I got this question, CDF and PDF related to things. So if somebody knows only PMF, Barnowler distributions, binomial distribution, so we can easily relate them with quantum measurement. PDF and CDF, they are highly related with the domain problems. So there is no specific region. Often people consider when they do a lot of quantum, like not quantum, just even any classical communication theory as well as quantum communication theory, lots of noise sources, independent sources, they often consider like Gaussian distribution, especially for the thermal noises, applying the central limit theorem and all. But there is no bar to explore other distribution functions. Say, for example, the Grover's algorithm. If you see how this particular Grover's search happens, basically it does certain reflection operations from one particular vector angle to another vector angle to find whether there is a phase change or not by with consultation with the oracle, right? And in that particular case, it assumes that the distribution of the angle is basically uniform, right? And in several cases for other algorithms, people have seen that gamma distribution is a better for certain applications. So it highly, I mean, it depends. There is no single answer for this. Okay. So with this, you can see that for the if lambda is pretty much small, so it is a bad approximation with normal distribution. But if lambda is sufficiently large, then you can say it's a good approximation to normal distribution. So suppose you are getting certain noise sources repeated, right? It's happening at a very high rate, okay, at some cryo chamber and some particular event, and that event is a discrete event. But in your experimentation, that is appearing as a continuous variable somehow, okay. So then in that particular case, you can consider this kind of situation that the repetition of some uncertainty event is very high with a constant rate. Then you are assuming approximating it with a normal distribution within the approximation error. Okay. So I mean, there are more theories, like there are applications of the things in the quantum regime, especially uh, today I did not cover statistical inference part, especially the hypothesis testing, maximum likelihood estimate, the maximum posteriori estimate like map estimation technique, and least square estimation technique. These are statistical inference theory coming from things like type 1 error, type 2 error, false positive, false negative. So these are the things tomorrow I'll slightly cover for 1 hour or 1.5 hours. Then I'll go for some quantum computing applications of probability and statistics, such as the quantum random number generator as an example. Then study of quantum noise and their analysis, and then one error mitigation example, although it will be more detailed by Dr. Ritojit. So I'll cover some of those aspects with some 50-60% theory and 50% coding, something like that. With this, I close the sessions today, and if you have any question, please feel free to ask me. I'll be happy to answer.
Thank you so much, sir.
Yeah, thank you.
Hello, am I audible, sir?
Yes, yes, you are audible.
Thank you so
See,
much for the insightful session.
thank you.
Uh, I hope the way participants have interacted means they have really enjoyed the session, even though you have earlier told that I was not prepared, but the way the session went on, it was, I think it was very interesting. Uh,
Yeah,
Everything, the mathematical, yes, sir, yes, sir.
normally I at least prepare some time that how to deliver things. It's not about the information, but also about whether people how they take it. At least from the angle of quantum computing. Today I could not prepare anything, but yeah, I tried. I hope they enjoyed. Yeah, thanks.
Definitely. Yes, yes, sir. That is the most important part.
Yes.
Classroom teaching, we all must focus on that part. Even though you have immense knowledge, if you are not able to deliver it in
Thank you so much.
a way, it is of no importance. So thank you so much, sir. And if participants, if you have any query, you may ask sir, or you may connect with sir on LinkedIn or via. Okay.
Yeah,
So
thanks.
the way the comment is coming, the session it really went well, sir. Actually,
Yeah,
they have really enjoyed the session.
yeah, thank you so much.
So,
So again,
okay,
see you
thank you,
tomorrow.
participants,
Yeah,
for showing your interest in the session. Although the session was very much mathematical, but you means sir has really made it for you. So thanks again. I think for
yeah, thank you so much.
today we are done, and And once again, I will just request all the participants to go and appear the quizzes that are live now. Okay. So quiz 1 and quiz 2 both are live now. Quiz 1 will be live until tomorrow midnight. Thank you, sir. Thank you, sir. So,
Thanks.
participants, you please go and appear for the quiz. Okay. Quiz 1 will be live until tomorrow midnight, while the quiz 2 will be live uh, by June